Welcome back, everyone. We're going to talk about bubble sort. I'm going to implement it in Python here. And this is the source code. I know a lot of people like to just come in here, grab the source code, copy and paste it into an editor and start working with it. So that's fine. You can do it here. I'm going to explain what all this is as we go through the rest of the video. But if you're only looking for the source code, here it is. Check the description of the video for the links to this in GitHub. We also have a optimized version of the bubble sort. So the one I just showed you was the completely simplified, bare bones basic algorithm. This one has just a couple changes that make it slightly better, but at the end of the day, you really shouldn't be using bubble sort in your production level code. It's just not very fast. There's much better sorting algorithms that are relatively simple to implement as well and perform better. Here's some sources. I got this slideshow, so it's a view-only, read-only version on Google Drive. So you'll be able to go down there and pull that up for your own, records if you want. Otherwise, the code's right here. You can click on that. I'll bring up Wikipedia. I referenced their definition for bubble sort. Then I also referenced the Big O cheat sheet, Visual Go, and TopTal visualizer. So what is bubble sort? Bubble sort is sometimes referred to as sinking sort. It's a simple sorting algorithm that repeatedly steps through the list, comparing adjacent elements, and swaps them if they're in the wrong order. It's a simple algorithm that performs poorly in real-world use and is used primarily as an education tool. Okay, so it's poorly in real-world use, primarily as an education tool. Normally it's brought up in like beginner computer science classes at the college level or so to introduce students to algorithms. It's just not fast, so that's why you don't normally want to use this in real world. Here's your performance. So basically bubble sort, given a list of n elements, so we'll say our list has 10 items in there. My best case is that it's going to take 10 computations to sort that list. All right, so the best case is, hey, the list is already sorted for whatever reason. I throw it into bubble sort to sort it again, and bubble sort realizes the entire list is already sorted. It doesn't have to do anything special, but it has to step through that entire list once before it knows that for sure. So that's why your best case is n, which is just a number of elements in the list. Other than that, your average and your worst case are n squared. And the reason for this is we basically have to step through the list twice. There's an inner loop and an outer loop. And we basically have to step through the list of 10 elements 10 times. Every single time I'm stepping through that list 10 times, I have to step through the list again. So I have to step through the list 10 times. For each one of those steps, I have to perform 10 more steps. So it's 10 times 10, 10 squared, or n squared. So average and worst case for a list of 10 elements would be 100 computations. This is from bigocheatsheet.com. Definitely check them out. I love bigocheatsheet.com. All right, how it works. So before we go into how it works, let's look at TopTal. It's a visualizer. This is a visualizer that up on the top axis here, a bunch of different sorting algorithms: insertion, selection, bubble, shell, merge, heap, so on and so forth. And at some point I'll do videos implementing all these algorithms as well. And then on the left axis you have basically what is the state of the list that's being sorted. So this row right here is all completely random lists. This one is a nearly sorted, so you can just see most of the elements in this row here. The list is already kind of sorted. This next row is a completely reversed list. And this row right here is a list that has a lot of roughly the same values. There's very few unique values in there. And we can look how bubble sort, we can click on these and we can see how it performs against these different types of list setups. So this is bubble sort on a completely random list. Here's bubble sort on a nearly sorted list. That was fast. Here's bubble sort on a completely reversed list, which would be the worst case. And here's bubble sort against few unique values. There you go. And if I want to get crazy, I can hit play all here, and that's going to show me, that's going to run all these animations at once, so you can really see how bubble sort stacks up against all these different sorting algorithms. So look, heap sort's done, merge quick sorts are done, insertion sort's done, bubble sort is now done, and insertion sort is done last, at least against a random list. Against a, let's look at it against a completely reversed list, which is the worst case scenario. So let's play them all again and pay attention to this row here. Okay, shell sort's done, merge, heap, quick, they're all done. Insertion is about done. Bubble sort's done, selection is done last. So that just shows you your different algorithms, how they perform, stack up against each other. Let's see, where were we? Alright, this is basically how it works. The idea is to sort an array in ascending order, such that the larger numbers bubble to the top. You heard the term sinking sort in the Wikipedia definition. That's because the smaller numbers sink to the bottom. And a little typo there, but it should say given an array list of length 5, you basically got to go over your outer loop 5 times, right? N, where N is the number of elements in the list. So iterate over the array of 5 elements. For each element, we need to iterate over the array, checking each element against each adjacent element. Adjacent being they sit next to each other. So 12, if I'm checking 12, the one I'm going to check is 37. Is 12 greater than 37? No, so we're good. Continue. But what about here? If I'm checking 37, then I'm going to check its adjacent element, 19, and I'm going to say, is 37 greater than 19? In this case, it is, so I would have to swap those, because 37 should bubble up to the top or the end of this list. Let's see here. And yeah, that's where your n squared comes from. So 5 comparisons for your outer loop, 5 comparisons for your inner loop. 5 times 5, or 5 squared, is n squared. Here's your pseudocode. Top version is a simple version. Just create an outer loop. Normally, people refer to that outer loop as I, but that's just convention. You can refer to it however you want. You're going to loop until the end of the array. You start an inner loop. Normally, people call that J. Again, that's just convention. You call it whatever you want. Loop until the end of the array minus 1. Do not include, that says last, or list index. It should say last, so I'll fix that here. Do not include the last index in the array. Okay? The reason we don't include the last index in this inner loop is because when I'm checking my adjacent elements, if I'm checking 19, I'm pointing right here to 19, and I say, let me draw a little, I like this thing. If I'm pointing right here to 19, I want to check the adjacent element. The adjacent element is here at 20. So I'm going to say, is 19 greater than 20? It's not, so good, continue. And then I'm going to move this big arrow right here. So now I'm going to be checking 20. Well, if I point here, so I'm including the last index in the array. Again, we don't want to do this. But if we do, you know, easy mistake to make, I'm to say, okay, well, let's compare this last index against the next index in the list, which is nothing, which is then going to give me a list index out of bounds error. So that's why we don't ever check, or our inner loop stops at 1 prior to the last index in the list. All right, let's see here. Yeah, do not include the last index in the list. And then if whatever we're pointing to, if whatever our J pointer is, the inner pointer, if we check that against the adjacent one or the one to the right of it, that's where that +1 is, right? To the right side of that number. Swap those values. Here's our optimized version. It's essentially the same, but this allows us to basically set our best case scenario to O to the N. So if I'm in this simple version up here, if I'm doing a completely sorted list, if you're giving me a completely sorted list to sort, I still have to do n to the squared operations up here in the simple version. However, in the optimized version, we only go O to the N, because basically I go through the whole list once and I say, hey, we perform no swaps, so therefore the list is already in a sorted state. So you create a variable to check if any swaps have been completed. I call that did swap. You can call it whatever you want. You still do your inner and your outer loops. Another small difference here is this right here. So now on our inner loop, we're only going to loop until the end of the array minus I minus 1. So up here on our simple one, we just did array minus 1. So not including that last index in the array. On this optimization, we loop to the end of the array minus I, which is the value of our outer loop, minus 1. And this, the whole reason we do this is basically we can always assume once we've done an iteration of I, that the value has bubbled up to the top. The largest value should already be in position. So we no longer need to check that last value again. So this just helps us do a few less iterations, but it's really not that not that much more efficient. And then down here, finally, if we're saying if did swap was false, so if we perform no swaps, we know that the array must be sorted, so we break out of the loop. So the did swap and breaking out if no swaps were performed, and then just also throw in this one extra, subtraction operator in there, optimizes the algorithm just a little bit. Here's an example. I'll pull this up. We'll talk about this, and then I'll bring up Visual Go, which is honestly, in my opinion, much better than what I can do here. All right, so here's my simple function. I got a simple bubble sort. It takes one parameter, the list that I'm going to sort. Here's my outer loop. So for I in range, I go the entire length of the list. Let me bring up my little editor here. Here's my outer loop. For I in range, I go the entire length of the list right there. Okay. And then in my inner loop right here, I call it J. And we go not the entire length of the list, right? We don't want to include this last index here. So I basically say loop until the length of the list minus 1. So this J is always going to stop at 19. And these pointers, the I and J, that's basically what I'm trying to visualize here. So here's my pointer. Here is my pointer. I is going to be this guy right here. And then J is going to be this guy right here. And on the next slide, let's go here. Go to the next slide here. Okay, now the next line we're adding is this. If list J, so here's J, is greater than J plus 1, right? So here's list J, here's list J plus 1. So this points to 17, J plus 1 points to 12, and I say, is 17 greater than 12? In this case it is, so I need to do something. But we're going to perform this check every single time. We're going to check what J is and compare it to the adjacent one or J plus 1. In this case right here, so here's what we're doing. This is a way to perform a swap. Basically, I'm just going to swap 17 and 12. In the code I have in GitHub, I use a function to do this, which in my point of view is a little bit easier to understand. But that's all that this line right here is doing. It's just swapping those two elements. And we'll see that in the next one. We'll see 17 get moved over here and 12 get moved over here. Here's my alternate swap. That's what I was talking about, the function right here. We're going to go over it in the code, so I'm not going to go over it now. All right, so there we go. So we performed our swap, and we've also moved our J, right? Because we got to the bottom of our inner loop. So we increment our inner loop variable J from 0 to 1, and we perform the whole thing again. Notice I stays the same. I is still 0. Okay, so now I'm going to say, hey, is 17 greater than 37? No, it's not. I don't need to perform any swaps. Okay, so that's what the next slide is. I didn't perform any swaps, so now I, again, got to the bottom of my list, incremented J from 1 to 2, and remember I is still 0 because I haven't completed this entire inner loop yet. Or, yeah, I haven't completed all elements of the inner loop yet. So now J of 2 is going to point to 37. J plus 1 is going to point to 19. Is 37 greater than 19? Yes, so I need to swap these two. Okay, so 19 and 37 are swapped. And notice this 37 is going to bubble up to the top, right? So now I incremented j from 2 to 3. J is 3. J plus 1 is 4, which is also the last element in the list. 37 is greater than 20, so we're going to swap these. We're going to swap those right there. And now notice we're going back to the start. So now I've incremented I, and j is reset to 0. So why do we do that? Well, remember, this loop right here, this inner loop, is going for j in range, the length of the list minus 1. So j is going to start at 0. We saw j start at 0 down here. And then we saw it go to 1, go to 2, go to 3. Right? Because the length of our list is 1, 2, 3, 4, 5 elements. Okay? So this is going to be the length of the list minus 1, which is 4. And the range function basically goes 0 up to 4, but doesn't include 4. It's exclusive. So that's the way the range function works. So this is always going to iterate just for j at least over 0, 1, 2, and 3. It's never going to go 4. Which is exactly what we want to happen because we never want j to be right here. Because if j is right here, here's my big arrow for j. And then my little arrow would be j plus 1. And I get a list index out of bounds because that doesn't exist. If I then try to perform this comparison right there. All right, so once this inner loop is finished, we increment the outer loop to I becomes 1, reset j to 0, and then we do this all again. So that's why you have to do the n elements in the list, so n squared, because I have to go through the inner loop and the outer loop completely every single time. All right, this will make more sense when I bring it up in Visual Go. So this is an awesome page too, and it has all sorts of stuff other than sorting algorithms. So highly recommend you come here and use it and support them as much as you can. But let's look at bubble sort. Okay, so this is a list of 1, 2, 3, 4, 5, 6, 7, 8. Let's just create our own, and let's create it equal to what we were doing here in this show. So 12, 17, 19, that's my sorted list, isn't it? This is what we started with, 17, 12, 37, 19, 20. So we'll say 17, 12, 37, 19, 17, 12, 37, 19, 20, I think was the last one, right? 17, 12, 37, 19, 20, 17, 12. Okay, cool. So this is the list we started with. And we can watch as it sorts through this. You can look over here and let's run this. Oh, I hit go. Okay, so I'll pause it. You can see it explains what it's doing here. And this is their pseudocode and they're kind of stepping through. Whatever line is highlighted is what they're doing. We'll watch it fast once. Okay, so that list is sorted. So let's watch it fast again. And then we'll kind of step through it one by one. There you go. So let's step through this. First thing we're going to do, compare 17 to 12. 17 is greater than 12. We're going to swap them. Compare 17 to 37. 17 is less than 37. We don't need to do anything. Continue. Compare 37 to 19. 37 is greater than 19, so let's swap. And now compare 37 to 20. 37 is greater than 20, so swap. And notice this one's highlighted in orange. That's because this element or this algorithm here is the optimized version. So it's saying, hey, I know that this highest value right here, this last index, is the highest value in the array. So next time you'll notice it doesn't even bother checking this. And that's why it has this, for I equals 1. So I is going to start at 1 to index of the last sorted element, which is 37 minus 1. So it's only going to go up to here. A little confusing. May take a little bit of practice before, and a little bit of drawing things out before that concept kind of sticks in your head. Let's see this one more time with a bigger list. So let's just create a random list. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 items in it. No, random and cool. Let's sort it. Let's just watch what it does. Okay, this is the first time through the outer loop. We're in the inner loop now, going all the way up to the end. I know that the biggest element at the end now, or the last element down here, is the biggest element. Okay. So now next time we only have to compare up to these two, 37 and 13. All right. Now I know that these last three are in the correct order. I only have to go up to 30 and 13, so on and so forth. So basically every time we go through this loop, this inner loop, we know that the highest number in the list bubbles up to the end. So that's why in the optimized version, you no longer need to check basically what you've already seen. That's how it works. One more time. .44 is the highest element in my list. Once I've done my inner loop once, 44 is at the last index. 40 bubbles up to the top. You're going to see 37 bubble up to the top now. Now you're going to see 30 bubble up to the top. You're going to see 28 bubble up to the top. 26 is going to bubble up to the top. 20 is going to bubble up to the top. Now we're ordered, we're sorted. So on that last iteration, it checked 1, it checked 4, it checked 6, it checked 13. It says, hey, I did not do any swaps. So the remainder of the list is sorted, so it broke out. So this is the kind of optimized version. Highly recommend. Go in here, play around with it. You know, create lists of whatever size you want and just kind of see what it does and how it reacts. All right, now we did that. So I'll jump into my code editor. Again, if you feel like you have a good understanding of what's going on and just want to look at the code, here's the actual code so you don't have to listen to my voice anymore. But if you want to stick around, I'll go ahead and code this up. All right, I got my PyCharm up. I have a completed version over here. All right, but I'll code it as I go. The first thing I'm going to do is my swap function. So it's pretty simple. Let's make this bigger so you can see, and I can get rid of that project pane. Pretty simple here. Just a function that I'm going to call swap. It's going to take the list that I want to actually perform the swap operation against, and it's going to take the indexes. I'm going to call this index left and index right, just so it's a little bit easier for us in the learning phase to understand what's going on. So I'm going to create a placeholder variable here, and this is going to be equal to one of the values. It doesn't matter which. It can be index left or it can be index right. It doesn't matter, but we actually need to store that in memory because basically we're going to perform the swap, and whichever one we use first, we're going to lose completely. So what I mean by that is, let's say we're in here on this, and I want to swap 12. Let me do one that actually makes sense. I want to swap 37 and 19. Okay, 37 is going to be index left, 19 is going to be index right. So if I go ahead and just say, hey, take that list and this index here, index right, set it to the value of 37. I'm going to get this. I can't do it because I can't edit that. Let me see if I can do it over here. I'm going to get 37 there. See, so 37 pops up there. Now I've completely lost reference to that 19. So I can never say, hey, take that 37 and set it to 19, because I don't know what was over here anymore. We know right now because we're humans, we have memory, but just like computers, the computer needs to throw this value here into memory. So basically what we're going to do is we're going to take this 19 or 37, it doesn't matter which one, and throw one of them into memory. So I'm going to go here and I'm going to write down 19. Now I can say, hey, copy whatever is in this left index over to the right index. So now I'm going to do that on my other screen where I actually have the permissions to do it. We're going to see 37 go here. Then I'm going to say, hey, that number that we just remembered, that number we threw up in memory, 19, put that in the left index. So if I didn't have access to this number in memory, this wouldn't work. So that's all this placeholder is doing. So then I would say, hey, take that number, throw it right there, and that's how you perform this swap. All right, let's bring up this again, and let me clear all my drawings. That's all this placeholder is doing. Taking a number, throwing it in memory. All right, next, all we're gonna do is perform our swap, which is pretty easy. We're just gonna say, hey, the list left or right index right, is gonna equal to whatever we have in the left index. So it's gonna equal to the list index left. Okay, now we're gonna say the list index left is gonna equal to that thing that we just threw out in memory. So whatever value is in our temp placeholder. And that's the swap function. Okay. Next up, let's do our simple bubble sort. So let's just define a function, simple bubble sort. Takes a list. Simple bubble sort. The list we want to sort. And I need an outer loop. We normally call that I. So for I in range, remember we're going to the end of the list, so the length of the list. Then I need my inner loop for j in range, length of the list. And remember, I don't want to include that last element in the list, so I'm -1. So length of the list -1. Then all we have to do is do a comparison. So if the list of j, so whatever we say in that see in that j pointer, is greater than the adjacent one, we can easily grab that by going j plus 1. Then I just perform my swap. So I call the swap function. I pass in, it needs the list. So I'll pass in the list as the first parameter. It needs the index that I'm working with, which in this case is going to be j. And it needs the index right, which is going to be j plus 1. Finally, I need to return the list. Oh, that's the wrong one. Here we go. I need to return the list, and I need to do it over here. So it's got to be indented underneath that outer loop. Okay? So see here, indentation level, indentation level. Common mistake is to throw this at the wrong indentation level, like there, or even there, and you're going to get some weird results. But here's my simple bubble sort, so let's go ahead and test this. In the example here, we used 17, 12, 37, 19, 20, so I'm going to create a list, and I'm going to do it in my screen here. I'll just call it unsorted list. Give me a second, and I'll bring it up on the thing you're looking at. 17, 12, 37, 19, 20. All right, so here's my unsorted list that I'm going to test, and let's just go ahead and do a quick little test case here. We're going to say print f string. Our unsorted list is going to become our, I'm going to do this here. My sorted list is going to equal to, I'm going to call the bubble sort function. And I'm going to pass in the unsorted list. But I'm going to do this little trick right here. You normally don't need to do this. I only need to do this because if I don't do this, it's going to make my test cases come out weird. And I can actually show you what's going on. So let's not include this. we're still going to get the list sorted correctly, so that's fine. Okay, so 12, 17. Notice this right here, which is my unsorted list, is actually showing me the sorted value, not this. Okay. And the reason for that is basically the way Python works underneath the hood. It's basically throwing this unsorted list in there. It's still inside of this function, keeping the reference to the same list and returning that list. So it's actually sorting this list right here. Really, normally we don't care, but just for this test case, I basically want to be able to see what my original unsorted list was. So if I do this little trick, this is basically going to say, hey, take this unsorted list, create a copy of it, completely separate copy in memory, and then throw that into the simple bubble sort function. So then we should see my test case print out correctly here. Run it again. There you go. 17, 12, 37, 19, 20 turns into 12, 17, 19, 20, 37, exactly what we want. Let's do some more test cases. I got some over here. I'm just going to copy and paste them in. Okay, so this is test case 2. We got 5 elements, including negative numbers. Just making sure this thing works with negative numbers. Run it. And -5, -100, 3,245, 10, and 2,532 turns into a sorted list. All right, got another test case over here. Again, one thing I always like to test as well is what happens if I pass in an empty list. All right, I shouldn't get any errors. All right, empty list is sorted, right? There's no elements in there, so can't be unsorted. But I just basically want to do this, make sure I don't get any errors. So let's run that, and no errors, so that's cool. So now that we've done this simple implementation, simple bubble sort, I'm going to go ahead and go down here and do the kind of optimized version. Now remember, we only have to do a couple changes here. And really, we won't see any of these changes reflected in our code. We could see them if we tested them against a large enough data set and then also timed it and checked how long each function took. But the end result is exactly the same. I'm going to get a sorted list. It's just this better or optimized bubble sort is going to perform it just a tiny bit faster. All right, so the first thing we got to do, the easiest one, is just say, hey, instead of going from for j in our inner loop to the length of the list -1, we're going to say length of the list minus j minus 1. And this whole theory right here, why we can do this, is because the largest number is going to bubble up to the end of the list. So I always know wherever I am in this inner loop, I can just see how many times we've ran I, basically how many times we've iterated over the outer list, and I can just go up to, I can subtract that from the end of the list and then finally subtract that 1 so I don't get that list index out of bounds. Okay, because remember, the first time I go through this, I is going to be 0. So I'm going to say the length of the list minus 0 minus 1. So literally exactly what this is saying here. Length of the list minus 1. However, once I becomes 1, now j is going to say the length of the list minus 1 minus 1. So minus 2. So I'm no longer including that very last index. When I becomes 2, this is going to say length of the list minus 2 minus 1, or length of the list minus 3, which is basically to say don't include those last 2 indexes. All right, just a small little optimization that says we know the stuff we've already kind of bubbled up to the top is already sorted, so I no longer have to do that. I'll throw a test case down here just to show you that this works, and then I'll throw the final optimization in here. Let's do better bubble sort, and let's get rid of these test cases here. I'll just comment them out. Okay, so this is all we're working with in our program. Let's run this. What do I got going on? Oh, because it's not j, it's I. That's a silly mistake. Not j, it's I right here. All right, so I still have 17, 12, 37, 19, 20. And it becomes 12, 17, 19, 20, 37. So it works. It sorted my list correctly. Okay. Again, we don't see any difference here in our output. I still get a sorted list returned to me. The only difference is underneath the hood, this performed slightly better. And I can bring out the debugger here if you want. It's already a long video, so I'll put this last implementation in and we'll see. I'll throw the debugger up if anyone is still actually watching at this point. All right, last optimization here is we need to check, did we perform any swaps? Because if I didn't perform any swaps, I know that the list should be sorted, right? And the easiest way we can do that is you can say has swapped. Technically, you don't need to, or did swap. Technically, you don't need to do this outside of this, because every time we go through this outer loop, I need to change that to false as well. So technically, we don't need this variable up here because I'm declaring it here as well. I like to throw it up there just because it helps me organize my thoughts. So did swap is false, and then I'm going to say, hey, if I'm performing any swaps, well, let's switch did swap is equal to true. So for each one of my inner loops, I say if I perform one single swap, I could have millions of elements in my list and I could perform only one swap, but then I'm going to set that did swap to true. And then I'm going to say if I iterated over my entire list and did swap was false. So I'm going to say if not did swap, I'm going to break. And that's it. So if I didn't swap anything, I'm just going to break, which is going to break out of this outer loop, which is then going to just jump down here to the return statement. Let's run this. And it works. Again, we don't see anything underneath the hood. All right? It does run faster. I'd have to bust out the timing module or something like that and test this against really large data sets to actually see the difference between the better or optimized bubble sort and then the simple bubble sort. And if anyone really wants me to do that, I can do that. You can jump in the Discord or something and ask me to do it, but I'm not going to bother doing it right now because it's already been a super long video, 37 minutes of craziness. All right, that's it. That's your bubble sort. Again, code is up here in the GitHub if you want it. Other than that, like, subscribe, I don't know. And send me a comment or something. I liked this or I didn't like it. Cool. And look for some more sorting algorithms popping up in the near future.